away we go.
Pilot chalk. Okay, there's some, not a whole lot, so.
That could truncate class as well. Okay, so today we're going to finish off chapter 2, and we're going to spend the whole time on a two-body problem. So this is an example that I brought up briefly before, but now we're going to get into it more deeply, and some interesting principles from physics are going to come out of this. So what we have is the actual two-body problem is a system of two second-order differential equations. All right. Now, the scalar r, which is also known as r12 in the book, but then at some point they changed to r. So like let's just have r from the beginning. And that's defined to be the magnitude of r1 minus r2. So the idea is you have, okay. If R1 and R2 are the positions of two objects, so this vector is R2 minus R1. This is an object of mass M1, this is an object of mass M2. G is gravitational constant. So given the gravitational attraction between them, based on these relationships here, because this is just Newton's second law, F equals ma. So the left side of these equations is the right side of Newton's second law, and then the right side is his left side is the gravitational force between them, which is proportional to 1 over the distance between them squared. So little r is this distance. Okay. So we're going to study these equations more in depth. Okay. Well, actually, I want to give the video audience a little more time to view this board. Because usually I just use this time that I'm erasing the other board, but this is the first board. So it's not the same thing. Okay. So, suppose I take the two equations over there and I add them. Now, what happens is, notice the right sides are exactly the same. Let's see, I think I'll tilt that a little this way. They're exactly the same except for one thing. You have R2 minus R1 in the first equation, and then R1 minus R2 in the second one. So if you add them together, the right sides are going to cancel out. So, yeah, so you're going to... So if you add two equations, you get, okay, M1 R1 double prime plus M2 R2 double prime is 0. Now, if we go ahead and integrate both sides, you're going to have, well, M1 and M2 are constants. So the only thing interesting about the integration is now you have R1 prime and R2 prime. And then what happens when you integrate 0, though?
It's a constant.
It's a constant. In this case, it'll be a constant vector called p. Now, r, each r1 and r2, those are positions. So, what is ri prime?
Velocity.
Yep. And double prime?
Acceleration.
Acceleration. Okay. Now, so this kind of test of who remembers little tidbits from physics. What we have here is what is mass times velocity? What does that refer to?
Momentum.
It is momentum. So this vector p is the
Constant.
yeah, well, the sum of all the masses times velocities. The sum of momentum of both bodies is the total linear momentum. But the key thing here is the left side is a function of time, but the right side is a constant vector. So, so what we're getting to that we have conservation of linear momentum. So the way you would actually define P is mass times the initial velocity, r1 prime of 0, and then same for the other body, r2 prime of 0. So you can use the initial velocities to figure out the total linear momentum, and it's going to stay that way. So r1 prime and r2 prime, those will change over time. But this particular linear combination of them has to remain constant.
So the initial momentum that they have.
Yeah, the initial momentum of the entire system is going to remain constant for all time, even though the individual momenta are they can change. Okay. Now, so that's the first thing I want to point out is that because it's constant, we have conservation of momentum. Okay. Now, though, suppose we take this equation and integrate it again. So on the left side, we're going to have m1, r1, so position, and m2, r2, the other position. So what happens when you take that constant vector p and integrate that? All integration is with respect to time.
So a PT.
Yes. And?
And a constant.
Yeah, we have to have a constant vector, which I'll call, whoops, b. All right. Okay.
What mass times distance?
Nothing special, really.
So B is just a constant of.
Yeah, it's just a constant vector, which would be obtained from the initial positions. Actually, well, okay, mass times position by itself doesn't have any particular meaning. However, we can get something meaningful from it if we just, so now what we do is, if I define big M is M1 plus M2, and now I'm going to scale, I'm going to scale this equation by M. So I have M1 over big M, R1 plus little m2 over big M, R2, and then I can divide everything on the right side by M. So I have, so V is equal to P over big M, and then C is equal to B over big M. Okay. Now, So what I have here, if you take your positions, alright, so this is also something from physics, although whether you actually saw it in your physics classes doesn't matter. It's also something I brought up in Cal 4, which one of you took from me. Except that now is integrals, not sums. If you take position, and you add up the positions, except you're weighting the position by basically the relative mass. So here it's like we have a mass fraction in each case. Because if you take these mass fractions and add them up, you're going to get 1. When you take the positions and you take a weighted average of them, and the weight is given by the mass fraction, what does that give you?
On the right hand side, there's a velocity vector times time plus a position vector, right?
So this is, so what we have is linear motion.
Okay.
So it's a constant velocity vector, and this is initial position vector. So what we're doing is we're describing the linear motion of some quantity, but what is that quantity? So,
All the objects with the mass m1 that m choose.
but this is, so the thing is, we have these two objects located positions R1 and R2, but now it's kind of like we're averaging them in some way. But it's not a straight average. It's not like R1 plus R2 over 2. It's not the midpoint. So masses of the objects are taken into account. And when it comes to gravity, and we're taking some sort of average,
Yeah.
anyone want to take a stab at it?
Stability, center of gravity.
Center of gravity. Yeah, or
because-
center of mass.
Oh,
Really.
so because they're coming.
I
You
was
were taking
imagining
that
those
point.
two little dots that he used to draw, and there's a formula for it.
So what would happen is, for instance, if you have like a huge object, like a huge planet and a tiny moon, then the center of gravity is going to be much closer to the planet itself because of its larger mass. So this, when you take a weighted average of the positions, and it's weighted by the mass, so this is the center of mass of an entire two-body system. Okay. So what this equation is saying is that whatever's happening to the two individual bodies, they might be orbiting around each other or something like that, the center of mass of the system, two-body system, is always going to have this nice linear motion to it. Even if the two individual objects have a curvilinear motion, the center of mass is going to behave like this. And this is the velocity of the center of mass, and this is the initial position of the center of mass. Okay. Now, so it turns out, though, that the center of mass is quite useful for studying the original two-body equations, because what we saw last time, we had an equation x and y, and we converted to polar coordinates, which led to separating the equations and being able to learn more about them, their solutions that way. So we can do the same thing here by making use of this center of mass. Okay. That's not what I want. Okay. So what I'm going to do is introduce what are called Jacobi coordinates. So right now the two-body problem has been expressed in terms of R1 and R2. And each of those has free coordinates because it's three-dimensional space. But so those are all our Cartesian coordinates. So the Jacobi coordinates are big R and little r, both vectors. So big R is just the center of mass. Okay. And then this vector little r is just R2 minus R1. So this has the effect basically of translating the entire system to be so that one of the objects is at the origin. All right, so it simplifies things for that reason. And just because the difference between the vector between the two objects comes up so often, you might as well express that more compactly. Okay. Now, on the previous board, we have an equation for the center of mass. It's Vt plus C. So let's look at big R double prime. So if we have big R, the center of mass, so I'll recall that is equal to Vt plus C. If you take the second derivative of that, what are we going to get?
Go back.
Yeah, we're going back to everything I did in the previous board. Well, what's the first derivative of that?
Just velocity.
V plus.
Yeah, just velocity. Yeah, it's v. So we take a derivative of that. Yeah, v is a constant.
Oh, so easier.
Yeah. So this helps. So this makes us. So right now it seems like we're getting a simpler system than before. But then we need little r double prime. Well, that's just going to be R2 double prime minus R1 double prime. And we have expressions for those, so we'll just go ahead and fill those in. Okay. So this would be right. Now, if I go back to the original equation, R2 double prime is GM1 over the scalar R cubed R1 minus R2. And then I have minus this, which is GM2 over R cubed R2 minus R1. Okay. So now, if I go ahead and simplify this, what I get is, well, the g over r cubed factors out. And then I have m1. Now, these are negatives of each other. So what I can do is, I can make this r1 minus r2. Actually, no, I'm not going to do that. I'm not going to change this one. I want to change this one. R2 minus R1. So that makes these the same. And I need to put a minus out here. Okay.
Then you can take the minus outside.
Yeah. So, there. So now I have, both terms are identical, except here I have an M1, here I have an M2. And then R2 minus R1. But what is M1 plus M2?
The total answer.
It's a total mass. That's big M from over there. So I have minus big G, big M over R cubed. And then R2 minus R1, that is just
R.
little r. Okay, so now what we have is, okay. Our new two-body problem So instead of equations for R1 double prime and R2 double prime, we have big R double prime is 0, and little r double prime is minus gm over little r cubed. That's a vector little r. Okay. All right. Now, the first problem for big R double prime, we've already solved that. Its solution is a linear function of time. So it's a motion of the center mass of a system. This problem right here is what we're going to spend more time on now. And this is an example of what's known as a central force problem. Okay. Now, a central force problem is still about gravitational force between two objects, and you're modeling those objects. It's just that one of the objects is at the origin, and what is happening to the other one. So it's basically the motion of one object relative to the other, because both masses may still be moving, but we're now changing our frame of reference by fixing one of the objects at the origin, wherever that may be.
But how does that help?
Well, it just simplifies things mathematically.
Coordinates of 0, 0.
Yeah, because now we're studying motion of one object instead of two.
Right.
Yeah. So even though it's technically still a two-body problem, it's like, well, how does one body move?
Right.
Okay. All right. Now, in the notes, I don't need to get into it here. So here we have big R and little r expressed in terms of R1 and R2. Now, R1 and R2 are what you really want in the end, but we're going to solve for these. So once you have big R and little r, you want to go back to R1 and R2. So in other words, you need to rearrange these equations. That's actually problem 1 in this section, which I meant to assign, but I actually just worked it out in the notes. It's not a very interesting problem. To invert these relationships, this is a 2x2 system of equations that you can invert. So like using a formula for 2x2 inverse, you get little r1 is big R minus m2 over big M little r, and r2 is big R plus m1 over big M little r. So that's how so now we can go back and forth between the two representations. So the idea is, you start with R1 and R2, we convert to these and solve these equations, because that's easier. Then we just change coordinates back. And notice, the way this is written, R1 and R2 are just the center of mass with some update to them, which makes sense, because both objects are oriented around the center of mass. Okay. Okay. So now what we can do is focus on the central force problem.
Is that R minus M1 over
Yes, minus for one of them and plus for the other. Yeah. Ah.
It's so cold.
I'm freezing.
Like I can't feel my legs.
Yeah, me either. But I couldn't feel part of one of them anyway, so.
The thing is, I keep bringing this up to somebody and nothing ever gets done. It's like,
It's the strangest thing.
And maybe we should just, I don't know.
You've been complaining for years.
Forget complaining, I'm just gonna go, I don't know.
I hate them.
Yeah, what do you do? Like
Yeah!
destroy the air
Maybe I
conditioning?
can bring a little space heater up here with me.
Yeah.
Can I do that?
I don't think there's any rule against it or anything.
I'll just bring one and plug it up and just right here. We use it.
That would be good. We can keep it in like your
I don't
know.
we should have
well,
done it
except,
with
except you're cursed.
I mean,
No, they make one. Oh, I saw this girl when I was at MC. She was in the library. It's like a fan kind of thing. It doesn't have any type of
And they make them to where you can't catch anything on fire.
yeah, it's like that. It's this
Like,
it's a fireproof, like it's a, don't give me that. Don't look at me like that. It doesn't, I'm telling you, it doesn't use, what the electric, the wire or
Yeah, I
anything
know
like
what you
that.
mean, wire.
It does, it's like a fan kind of thing, but it, like, draws out the, I don't know, it's,
You'd find a way.
I'm gonna buy one because I'm tired of freezing my butt off in class. It makes me not want to be here, just because of the cold.
Well, at least you have the videos.
but it's not that cold. I mean, it's cold, but I mean,
You're not me!
well, of course not.
You don't
Of
understand!
course not. I mean,
You do not. My apartment has been on 79 degrees for the last 4 days.
you are very
Not everyone is lucky.
Okay.
I mean, you are sitting right there.
Is that where it comes out?
I mean, it takes the air.
Yeah, I think if you go back a little bit.
I was freezing over there.
I'm almost cold in here.
I'm cold everywhere. I was cold this morning when I walked outside.
Anyhow.
Well, it was
If
cold.
it's from here, you should.
Yeah,
That's
it was like
spicy.
chilly.
Glass
That's
is spicy.
Well, it'd be
compared
really,
to us.
it'd be really, yeah, but it's just gonna be hot by the time the winter comes.
Okay.
You know how it gets in
So the general
here. You get, like, stuff
central
like
force
that.
problem
Yeah.
is this. Okay. So what we have here, for equation for little r on the previous board, is just a specific example of that. So in our case, find little m to be m1, m2 over m1 plus m2. So that is called the reduced mass. Okay. So in that case, we have, and our double prime is minus g m1 m2 over r cubed r. And so the reason why we have the division by r here in the general case is this here is a unit vector, so we have only direction. Okay. So all I've done here is, if you take our previous problem for our double prime and multiply both sides by m1, m2 and do some rearranging, then this is what he gets. So this is equivalent to the previous equation for little r double prime. But I'm writing it in this form so that we have an expression for our function f of r, which is meant to describe how the gravitational force varies as a function of distance. In this case, it's g m1 m2 over r squared. So it's just the inverse square law. So we can study this problem with any choice of f of r, but this is what we're using for gravitation. Okay. All right. Oops, these are wrong notes. All right. Okay. Now, before we study this equation in depth, just one more point I want to make about the other quantities that help us understand the motion here. If I have my curve as so my position vector r, right? Okay, so I'm studying it. What's going on at a particular point in this curve? So this is r sometime t naught, and what I have here, the tangent vector, is r prime at t naught. So if I consider this vector R cross product with MR prime. Now, if you take a cross product of two vectors, what kind of vector do you get?
Dot product. Wait, cross.
Cross product is a vector, but what property does that vector have? Does anyone remember from calculus or physics or whatever?
It's the row and column.
Well, how you compute is like a 3x3 determinant, but the vector that you get is orthogonal or perpendicular to both vectors.
Right.
So you're going to get some vector here. Now, these vectors are, okay. So if this is your, let's say the origin is here. So this is your position vector, and then here's your tangent vector. So this might be your cross product that's perpendicular to both. So this is M, so this is R cross M R prime. Okay. Now, let's take this vector R cross M R prime and take a derivative of it with respect to t. Okay. Now, how do you take the derivative of a cross product? You might think, oh, I got to use a product rule, but it's not a regular product, it's a cross product. But it turns out that something very much like the product rule applies. So you can think of it that way. So this would be like R prime cross MR prime plus R cross MR double prime. Now, the cross product of two vectors that are parallel is always 0. So that's gone. On the other hand, MR double prime, I've had written over there. That's the left side of that differential equation. So MR double prime is, I can substitute the right side. Minus f of r over r, which is just a constant, times r of a vector. Well, once again, you have a cross product of two vectors that are parallel. So that is also 0. So what that means is the derivative with respect to time of this vector is 0, therefore the vector itself is
A constant.
it's a constant vector. And I'll call that vector L. Okay. So what this is, what we're seeing here is conservation of angular momentum. Okay. Because what is momentum? Mass times velocity. Here we have mass, reduced mass, times a velocity vector. So this cross product is giving you not just plain momentum, but the angular momentum. That is always a constant vector. Now, what does that mean? So this vector, which is a vector L, is no matter where the object is going, that vector is pointing in the same direction, same magnitude, same everything. So so the motion of this two-body system remains in the same plane. So what we observe from planetary motion, we have all these planets orbiting around the sun, and that motion it's an elliptical orbit, but it's staying in the same plane. So, because you would think, well, if there's some gravitational force, there's no reason why the why the planet can't just spin into different planes, but it doesn't because of this. Okay. All right. ugly.
Yeah.
Okay. Page and a half to go. So now what we'll do is we'll revisit the central force equation, but in polar coordinates. Okay, so our central force equation, we'll just stick with a general one. R double prime is minus K F of R over R times a vector R, where in this case, K, just for convenience, is 1 over M. Okay. All right, so now we do polar coordinates. So X, so we'll now X is R cosine theta, Y is R sine theta. Now, all along I've been saying this is a three-dimensional problem. But I'm treating this as a two-dimensional problem. You think 3D problem, maybe I should use cylindrical coordinates or spherical coordinates. How come it's okay to reduce this to a 2D problem? Why am I justified in doing that?
Because of that thing.
Yeah, conservation of angular momentum. You're staying within one plane. So what you can do is, even though that plane is not necessarily like the XY plane, it's like you can change the variables so that you can rotate things so that you are in the XY plane, and then if you need to, rotate back. So this is not an oversimplification because we're confined to one plane. Okay, so now I'm going to write this equation, break out two equations in terms of components. So x double prime is minus k f of r over r x. And y double prime is minus k f of r over r y. And r is now the square root of x squared plus y squared. Its usual meaning in polar coordinates. So what I'm going to do now is I'm going to take these two equations for x and y, and I'm going to carry out their differentiation. Now, so for instance, x prime is r prime cosine theta minus r sine theta, and then similar for y prime is r prime sine plus r cosine. And then what you can do is differentiate them again to get expressions for x double prime and y double prime. So I'll just write out x double prime. They're both in the notes, but and both similarly ugly. So for instance, so now what I have to do for x double prime, I have to apply the product rule again to both terms. So it's going to get nasty. So for instance, for x double prime, I'd have r double prime cosine. Actually, I'm doing a chain rule, so I need theta primes in these two terms. So here, for instance, I need r double prime cosine minus r prime sine theta, theta prime, and then when I differentiate this, I have to use a product rule, and that's going to give me three terms because I have three things multiplied together. So I have minus r prime sine theta, theta prime, but these two terms are going to combine to give me minus 2 r prime sine theta times theta prime. And the sine has only been taking up a theta. And then I have to do the rest of a product rule on this. So minus r cosine theta, theta prime times the other theta prime. So that's theta prime squared. And then finally, minus r sine theta, theta double prime. So all of that is x double prime. And then y double prime you work out in the same way, product rule on these guys. Okay. So what you can do is take your expressions for x double prime and y double prime. So like I would take this and substitute it back. Got enough arrows here? Into here. And I'd also replace x by r cosine theta. So what you can do is, now the f of r over r, you can leave that the same. But the idea is, by carrying out this differentiation, you can get rid of x, all traces of x and y, and write all of that in terms of polar coordinates. Okay, so in spite of all my arrows, does a process make sense at least? Well, and also you can read about it in the notes. Okay. So y double prime is actually, yeah, it's essentially the same as this, except wherever you have cosine, you have sine, and then some of the minuses become pluses. That's the only difference. Okay. So it's just a lot of chain rule and product rule. Okay. So now I'm in a position to.
So do we write those in terms of like x double prime in terms of
Yeah.
r double prime then?
Yeah, so what happens is, try not to have a disaster here. What?
Please call it out.
It'll get you on a creeps of one when you're finally
I just
so.
put my hands one. You guys are right.
Yeah, and the thing is, I never feel it because I'm moving around, but if I stay still long enough, I feel it too.
We're not allowed to move around.
Yeah, so for instance, x double prime equals minus k f of r over rx becomes, okay, r double prime minus r theta prime squared cosine minus 2r prime theta prime plus r theta double prime. So all of this is x double prime
Right.
equals minus k f of r cosine theta. And this is minus k f of r
Over our x.
over rx. And the thing is, x is r cosine theta, and that r cancels with this r.
Right.
Okay. So now it's the left side of this equation that's messy. And then we have similar for y. And so r double prime minus r theta prime squared sine plus 2r prime theta prime plus r theta double prime. Oh, dang it. Supposed to be a sine here after all that, and then a cosine here. And then all the other stuff. So k f of r cosine for x, and k f of minus r sine for y. Okay, so that's what these equations are now in the polar coordinates. And what you do now is, it's kind of similar to what we did recently with limit cycles. Where you can take these equations in polar coordinates and take linear combinations of them, like you can add them, or multiply by something and add them. So what you can do is, if you multiply by cosine, multiply the x equation by cosine and the y equation by sine, and then you add them. Well, what happens is you're going to get this times cosine squared plus this times sine squared. These will cancel out, And these also will have a cosine squared plus sine squared. So what you end up getting is r double prime. So what's in here? R double prime minus r theta prime squared is equal to minus k f of r. So that simplifies dramatically. On the other hand, if you multiply the x equation by sine and the y equation by cosine, and you subtract, what will happen is, so here you have cosine times sine, here also cosine times sine. These parts will cancel, and these will stick around, and these will cancel. So what's left is 2r prime theta prime plus r theta double prime is equal to 0. So now you transform the system yet again by taking advantage of conservation of angular momentum to put everything in 2D and therefore polar coordinates. The second equation in particular is one that we can actually solve. Okay. But yeah, it's kind of funny how what happens in a class of this level, really what you're doing is you're still working with lower level things, except now you're combining them in very different ways. Because people might think a higher level class like 605 must introduce a whole lot of brand new math. Not really. It's more like finding different ways to make use of lower level math. Still means it's a pain, but yeah, everything there is just what we've done the last few boards is product rule, chain rule, trig identities, algebra. Okay.
What does the first equation tell us? Like, just r prime, r double prime equals r.
Okay, let's see, do I talk about that one later? Because I'm going to deal mostly with the second equation, but
Yeah, but that's going to come out as Kepler's second
yeah.
law, right?
The second equation is, yes. And then once you have that, then you can use that to solve the first equation and actually figure out the planetary motion. So, yeah. Okay, so let's finish this off in the last 17 minutes. Okay. So, I'm going to take the second equation over there, and I'm going to multiply both sides by r. So 2r, r prime, theta prime, plus r squared theta double prime is equal to 0. Now, in this form is where it's easier to solve, because 2r r prime is the derivative with respect to t of r squared. Because r is a function of t, differentiate that, you get 2r from power rule, then chain rule gives you the r prime. So this is, but here we have just r squared, undifferentiated. So this whole thing is a product rule in reverse. So we're going to get r, so the derivative of r squared theta prime is 0. Because in this term, the r squared is differentiated. In this term, only the theta prime is differentiated to give you theta double prime. So now you integrate both sides of this, and you get r squared theta prime is a constant. And this is Kepler's second law. Now, mathematically, you're like, well, what does that really mean? It doesn't help us very much. But it turns out by working with this a little bit, we can get a useful interpretation. So now what I'm going to do is I'm going to take both sides of this, and I'm going to Well, I can multiply by 1/2 and integrate with respect to t. So from time t1 to t2, r squared theta prime of t dt is equal to, now if I integrate this with respect to time, I still have the 1/2 because multiplying both sides by 1/2 c, and then I have just t2 minus t1, because when you integrate a constant, it's just the constant times the difference of the limits. Okay, now this kind of integral you've seen before, but not lately. It comes up in Cal 3. This is the area swept by a function r is equal to, r equals r of t, from between the angle theta of t1 to the angle theta of t2. So what happens is, in polar coordinates, so this is r is equal to r of t. This is the angle theta of t1. This is the angle theta of t2. So this integral gives you the area. So this is the area of a polar curve. Okay. So, but notice the right side only depends on the time t. So what this is saying is that equal areas are swept out in equal times. So what could be happening, for instance, if you have, let's say this is your planet's elliptical orbit. Well, actually, I'll make it more exaggerated so it'll be easier to see. Okay, something like that. So you look at this area that's swept out here between these two times, and okay. So the idea is these areas are equal. The time spans are equal. So, because you might think, well, the distance along this orbit here is longer than this. So you might think it will take longer to sweep out this distance than this distance, except the area is, the distance away from this body, like the sun in this case, is larger. So what's happening is, even though it's traversing a shorter distance, because it's further away, the gravitational attraction is less. So it's not moving along as rapidly. So equal areas are swept out in equal time. So that's what Kepler's second law is saying. Okay. Now, so at least from the second equation, we can get some nice insight about the behavior of the orbiting object, but we still like to be able to solve the equation. And during what time we have left, we'll see what we can do. And in fact, we can make some headway by performing yet another change of variable. So first we changed to, this is our third coordinate change. We changed the Jacobi coordinates to simplify the system. Then we confined it to a plane. And let's switch to polar coordinates. We've got simpler equations still. And got Kepler's law. And now we're going to make one more coordinate change. And then I'll be really sick of doing it. Okay. So, in order to help us solve the other equation, which is r double prime minus r theta prime squared is equal to minus k f of r. And I'm going to simplify the assumptions a little bit. I'm going to let f of r just equal 1 over r squared. It has not been this. Before it's a constant over r squared, but that's not really, so it's not really a big deal to make this simplification. Okay. So, my change of variable is I'm going to let rho be defined by this relationship. So r is equal to 1 over rho of theta. So now the thing is, r and theta both depend on t, but I'm really going to say that r is a function of theta now. So it's still going to depend on t, just indirectly. So that way, if I can solve for r in terms of theta, and then I can solve for theta, then I have everything I need. Okay. What I can do now is differentiate this. So r prime is 1 over rho squared times rho prime of theta times theta prime. But I can rewrite this. Oh, there's a minus there. Yeah. Well, 1 over rho squared is r squared. So I'm going to put the r squared and the theta prime together. And then I still have the rho prime. But I have Kepler's second law. So r squared theta prime is c. So in fact, r prime is a very simple expression now in terms of, so that it's just minus c rho prime. And that will help a great deal because now I can take a second derivative, and that's just going to be minus c rho double prime, but rho depends on theta, so it gives me theta prime. But the thing is, I can use the fact that r squared theta prime equals c, so that tells me that 1 over rho squared theta prime is c. So that tells me theta prime is equal to c rho squared. So I can just get rid of theta prime altogether and get so I have minus c squared rho squared rho double prime. Okay, so that way I've gotten theta out of the picture entirely. So now what I can do is use this in this equation. So the idea is I want to get an equation in terms of rho. So now what I have minus c rho squared rho double prime minus, now the thing is I have r theta prime squared is equal to minus k. Now, f of r is 1 over r squared. All right, so far I have everything written that way, but I want to get rid of all the r's and replace them with rho's. So, c rho squared rho double prime, and r is 1 over rho, and theta prime is c rho squared, and 1 over r squared is rho squared. So now I've gotten rid of r completely, but now I need to simplify this.
So it's negative c rho squared?
Well, first, notice I have minuses everywhere, so I'm going to cancel all those out and get pluses. Also, Rho squared, I have here and here. So I'm going to cancel those out. And then I have to divide this by rho squared to keep everything consistent. Okay. Then I'm going to divide through by, let's see. Oh, sorry, that should be a c squared. Okay. I'm going to divide through by c squared. So now I have rho double prime plus c squared rho to the 4th over rho cubed equals, okay, so now I have that. So now I have, finally, rho double prime plus rho is equal to a, which is a new constant I've defined to be k over c squared. Okay, so now so this equation simplifies dramatically. Well, I should include the right side of that. Okay. So all this is I'm using Kepler's second law to get rid of all the references to R. And also simplifying my derivatives. And then here I'm just expanding everything out and trying to get the simplest expressions possible, just canceling whatever I can. And then I wind up with this.
What's a here? A constant?
Yeah, a is just a constant. And it's defined to be k over c squared. It's just a convenience.
Right.
Okay. Now, this equation, I've got 3 minutes. This equation you can actually solve. So, how would you solve this? This is something from your first DE class. It's non-homogeneous. You got to use the method of undetermined coefficients. But it's one of the simpler cases. So you get a constant A plus a constant times cosine theta plus another constant times sine theta. So now I have an expression for R. So R of t is just 1 over that. Where you keep in mind that theta is a function of t. Okay. So now we have R. But how do you get theta? Well, for that, use Kepler's law again. And I've rewritten that over here. Theta prime is equal to c rho of theta of t squared. So, but the thing is, now we know what rho of theta of t is. You can take this and substitute it in there. So now theta prime is equal to that. In this case, at least now we just have a single first order ODE. Now, it's not something that's actually easy to solve because you have cosine and theta, cosine and sine of your dependent variable, but you can try solving it numerically, for instance, like using Euler's method or better methods. So at least we have a practical way to use a numerical method after mostly analytical work in order to find a solution and trace the orbit. So this is how we can figure out planetary motion based on the masses and initial positions of the objects in question.
So you're putting in that row for theta t.
Yeah, so I would fill in the form of rho here. So this would be c times little a plus big A cosine theta of t
Right.
plus b sine theta of t. So now I just have one ODE.
And they'll all be squared, right?
Yes, the whole thing is. Yes, the whole thing is squared. Yeah.
Right.
So that makes it a little uglier still. But then you're using, but by thinking in terms of its integral form,
So you integrate this to get theta of t
yes.
in terms of t. Theta.
Yes, yeah, you get theta t, and now you can plug that in here to get r of t. Yeah. So.
Yeah.
Yeah,
Are
so
we
still,
going to use that in our homework?
no. No, homework's will be easier than that. So you don't have to solve that equation in the homework. No, that's a computer's job. Okay. Yeah, so not the most satisfying conclusion, but that's because we're dealing with a problem that at its core cannot be solved analytically. But at least analytically, we could get to a point where what you're doing numerically is a whole lot easier than at the start. If we just took the original form of two-body problem. I mean, you could apply a numerical method to that too, but except it would have stayed a 3D problem. Now we've reduced it first to a 2D problem, and now really just to a single ODE. So that's why it's really nice to do a combination of analytical and numerical work to make a numerical problem simpler if you can. And now most of you guys get to go to real analysis.
And I get to go to my office.
Lucky you.
Get to go through analysis. You realize that you said that, right?
Yes.
Have to go.
Yes, but I can be sarcastic.